Hello, welcome to Maps of Math. This is a video in the Geometric or Clifford Algebra series. Today we're going to talk about orthonormal bases calculations in geometric algebra. So we'll do mostly focus on trying to get the dimension of a geometric algebra. The vector space V has dimension n. What is the dimension of the Clifford algebra? And just get a little more computational. We've been very categorical so far. So pick an actual basis and try to calculate a few things. And then we'll, in the rest of the series, continue doing categorical stuff for definitions a lot of times, but then I'll also make sure to get into bases and try to calculate specific things and actually get our hands dirty, as it were. Okay, so remember in forming a Clifford algebra, we've got some quadratic space V with quadratic form Q. We map it to, I guess I'm mixing terms, but I'm using the fancy G for some reason in this video. I just decided to instead of the CL. So we get the geometric algebra generated by this quadratic space. And if you remember, that is the tensor algebra generated by V, quotiented by the ideal generated by the tensor product of V with itself minus quadratic form on V times the identity in that algebra. So this thing ends up then being an algebra. That is our Clifford algebra or our geometric algebra. And if we remember, this thing is universal in the following way, where for any other algebras A and for any maps from the vector space V, so here V is fixed in all of this, for V into the algebra A, where U is the forgetful functor applied to the algebra, so it just means the particular forgetful functor is forget the multiplication. So we're just looking at the algebra as a vector space. And so phi then is a linear map, right? So from this vector space to this vector space, the algebra forgetting multiplication. So it's universal in such a way that for every one of these A's, there's then a unique phi bar that's an algebra homomorphism from A into oh, this is going the wrong direction. G is initial. Oops, that arrow's the wrong way. At least I caught it in the shooting, so let me get the direction of it right. Oh, my thing's being super slow for some reason. So it's supposed to be that way. At least I got this right. So over here I drew it the right way. So we get this unique algebra homomorphism from from the geometric algebra into this. Oh, this is again wrong direction on this arrow. Where then this V is you do the embedding of V into the Clifford algebra, forgetting the multiplication structure, and again this is then forgetting the algebra homomorphism. It's a linear map now. So instead of paying attention to the multiplicative part of it, we're just looking at the linear structure part. Fine. I bungled that explanation well enough. And just to hit it one more time quickly, as I've done in other videos, we really have this common category where it's actually this common category with this particular condition. And so it's the Clifford algebra is initial in there. That's entirely equivalent to what I just said. Okay, go watch the other videos if you want a better explanation of that. But let's get into the orthonormal bases, the focus of this video. So now let's take some orthonormal bases. So we've got VQ. If Q is not characteristic 2, you can always get an orthonormal basis. I think that's right, unless I'm making that up. Sometimes my brain does not function terribly well in these videos. And the orthonormal part, the normal part of it is that Q of EJ, it's 1 of +1 - 1 or 0. So this video will be agnostic to what the particular signature is. So here we can always diagonalize Q. Actually, I even put the I think here, so I didn't bother to double check. But I'm pretty sure it's right that you can always diagonalize as long as its characteristic isn't 2. Someone in the comments can tell me if I'm right or misremembering that. And again, we are also signature agnostic here, so we don't need to specify. Usually, you specify these, P, Q, and R, where this is the positive part, the negative part, and the degenerate part of the signature, and they add up to n. We don't have to specify here. This is all the stuff we're going to talk about is going to hold true regardless of what the signature is. So fine. So right off the bat, the defining relationship that we've used to generate this Clifford algebra is that for each of these, for any vector, but in particular for each of these bases elements, this orthonormal basis, EJ squared is going to equal the quadratic form on EJ times whatever the identity is. In particular, this thing is a scalar, right? This is just some number. But then I'm just going to start saying R, but it's whatever our base field is. But let's just say R times 1. So this is just some number, whatever this is equal to. Oh, and notice I'm also starting to mix. I'm just writing EJ, whether we're actually talking about the original vector space V or the image of a vector V or vector X, whatever, inside of the algebra. So this is in the algebra. This is in the vector space. So I'm not putting like some hat or like some alpha or something to indicate that this has been moved into the algebra. So just, if I start doing things like multiplying vectors, assume it's in the algebra. If I start talking about the quadratic form on it, assume I'm talking about back in the vector space. So, okay, this gives a scalar. This is evaluated on the vector space side. This is the identity in the algebra. Do recall you can always form from little q symmetric bilinear form. In this case, I wrote it as a little b. Under this formula, this is the polarization identity. I actually led myself down a little bit of a rabbit hole because I did double check this to make sure I wasn't misremembering stuff. So Q usually comes from some sort of bilinear form that doesn't necessarily symmetric. So I'm calling that capital B. There is the fact that if Q is not coming from some bilinear form, capital B, where then Q of X is equal to capital B of X comma X, then we do actually have to require for Q that this induced B be bilinear. Like the properties of a quadratic form by themselves won't make this thing in particular linear in each argument. So that, So here's how, if we have this not necessarily symmetric capital B, this is how Q is defined. If that's so, then this formula turns out to just be this. And this is then just the symmetrization of the not necessarily symmetric. Is this supposed to be a plus? That's supposed to be a plus. Oh my gosh. Well, I hope somebody would have caught me there. But that's supposed to be a plus. That would have been the anti-symmetric one, which I don't want. So that's the symmetrization of B. Anyway, the whole point of bringing any of this up is we're just going to use this rearrangement of this in 2 seconds. So let's just use this to get the one extra crucial thing we need. Let's take two basis elements, assume J and K are not equal. Well, by the defining property, we get this, and substituting in for that equation we just had, we'll get this out here. Now, this is orthonormal, so the induced symmetric bilinear form B, little b, that this is 0. So we're just left with these two, this times 1, this times 1. So pulling those over to the left-hand side, if we then expand the multiplication, EJ squared, EJ, EK squared, and then you get the cross terms. Well, this is equal to this is equal to this. So we cross them out, red with red, blue with blue. And so then 0 equals this. So in particular, for J not equal to K, for an orthonormal basis, we get this key relationship, which just says that the multiplication then on individual orthonormal basis elements is anti-symmetric. This is really key because it's going to let us move stuff around. And this is why we work in an orthonormal basis, because it kills the cross term. Let me show you what this, the implication of this. So we got two things we're going to work with here. Again, vector space or quadratic space V, pick an orthonormal basis, whatever signature it may be. The EJ squareds are either 1, -1, or 0. Doesn't matter. We've got that, the EJ squareds then also equal this scalar in the Clifford algebra, and that we can swap orders of two different basis elements. This is going to make it so that anytime we have a repeat basis element, we're going to shrink down in dimension. So if you have a bunch of the orthonormal bases in a product, and it's geometric products, if we have any repeats, they're going to reduce, and so the product's going to shrink. And in particular, this is what's going to let us move stuff around to then, if we've got EJ here, EJ over here, and then a bunch of other stuff in between, you can swap stuff until they come next to each other, and then it'll drop dimensions. And this is going to be the key that's going to make it so that the geometric algebra is not z graded or n graded, but it's not going to respect that, as I'll show in a second. Like you can have a degree 1 times a degree 3 and get a degree 2, for instance, as opposed to a degree 4. So show that in 2 seconds. Actually, show it right now. Okay, never mind. I'm getting ahead of myself. So say I've got, this is in the geometric algebra. I got this product in the geometric algebra. Well, when I put them together, I can swap the order of this with this. And all I do is get a negative sign out in front, right? I just get a scalar, and I can pull scalars out. So I get this, and E1 times E1, well, it's whatever Q of E1 is, but this in particular is a scalar. So I got a negative times this scalar with this. So in particular, what I was just saying, degree 1 times degree 3 is now giving something degree 2, where the degree here is the number of linearly independent vectors in a geometric product. This would not happen if the geometric algebra were actually n-graded. Like the product of these two would be degree 4. And this is part of what happens that makes the geometric algebra interesting, is you can get deformations that play with the degrees. Yeah, okay. Again, no z grading. I apparently keep getting ahead of myself a little bit and saying some of the comments. Okay, let's ask a quick question as we're driving towards the completion of this video. If the dimension of V is n, what is the dimension of the geometric algebra generated by it? So remember, by definition, I guess by definition, but we tried this and figured out that it has the right properties. It is initial in the way we need. So this is what is the geometric algebra, and it's unique up to unique isomorphism. So it's a quotient on the tensor algebra generated by V by this quotient. Now, let's remember, tensor algebra. What is it? Well, it's the field, direct sum the vector space, direct sum, degree 2 tensor product of the vector space plus degree 3 on up for infinity. And so the basis here and what spans it, like the number 1 is going to span this, whatever the identity is. Our E1 through ENs are going to span this. Our tensor products of EJ with EK, where repeats are distinct. So like this is E1, E2, that's different than E2, E1, for instance, and so on. So obviously this thing is infinite dimensional, and it's big, and there's no restrictions, as I'm saying here, on any of these things. Why do I bring this up? Well, first, let's just highlight that mapping from V into its generated geometric algebra, that's a surjective map. This is a quotient map. So if this set spans the tensor algebra, its image certainly spans this. Okay, so great, our upper bound is that the vector space is infinite dimensional. Well, we'll see in 0 seconds that the two relationships, the ability to swap orders of different orthonormal bases, and then the reduction that will happen if you get two of the same next to each other, are going to now make this at least finite dimensional. So to start with, I got no restriction on the J's and K's here, right? This at least spans. And notice here, I'm not writing the tensor product in here like I did a second ago. This is now assume the geometric product. Usually the geometric product, we just write things right next to each other. So this is EJ geometric product with EK. Okay, so now let's just look though. If I've got some product of this orthonormal basis, remember this is all an orthonormal basis for V that we're assuming we've already picked. If I've got a product of them where the number is greater than n, the dimension of the vector space, then I'm gonna have repeats of the EJs, right? There's at least some repeats. So the point is, well, then we can rearrange. We can use this relationship to swap orders until we get repeats right next to each other. And every time we get a pair of repeats next to each other, we get a collapse. And so this, we'll swap them around, square it. This will be a scalar, so we'll shrink down. So this is going to be equivalent to and reduced down to some other product of orthonormal from the orthonormal basis, but where L is strictly less than or equal to n. So already we're finite dimensional. This is now going to take the big, anything above degree n, all of those potential combinations of orthonormal vectors in the geometric product are going to now get mapped down into, they're collapsed into the degree n or less camp. Okay, so we've shrunk our spanning set to be at most this big. So we're at least now we're at least finite dimensional, but we get further reduction because we know that if you have like E1 geometric product E2, that is not linearly independent of E2 geometric product E1 because you can swap them and you get a -1. So one is actually -1 times the other. So we're actually going to get even further reduction. And in particular, the only things that are going to be linearly independent are strictly increasing uh, indices. See, did I write it any better than I just said it? We got this, and basically we take the list on up. The EJs just stay all there, but like if we look at the product of two, it's going to require J and K. J strictly less than K, K less than or equal to N, J less than or greater than or equal to 1. So this is strictly increasing, and it's going to go on up for all of them. So like when you get to the N term, the only linearly independent product of the orthonormal bases that's of degree n is just it's just one of them. Pick one of them. All the other ones are linearly dependent. So we're fixing the ascending convention. Just like pick one order. So you could pick a different order. There's nothing canonical about like which one we picked is E1 versus E2. But it's like you pick E1 through En, put them in order. That's the one. There's only the degree n is one dimensional, right? This could be a basis vector for it. Is the point. So just to make anybody who's done combinatorics, this is now equivalent. If you let S be the set 1 through n, you take J as some subset of S, and let's have E sub capital J be a product of the elements in J, where J1 through JL they are the things that equal J. Well, then the collection of these EJs for J, a subset of S, this is what spans the geometric algebra. Generated by V. So you could say, well, what's the dimension of this? Well, this is all the different subsets of here. It's just the power set. So if this has got n elements, the power set has 2 to the n, which is what I say here. So if this has n elements, then there are 2 to the n subsets of it, including the empty set. So we've got the dimension of the geometric algebra is less than or equal to 2 to the n. It's actually going to, as long as the field isn't characteristic 2, I think that's the only restriction, then the dimension actually is going to be 2 to the n. Just to start talking then about the different degree levels, and let's just pick a specific one. So let's say we've got R3, we pick an orthonormal basis, E1 through E3, then we got degree 0, degree 1, degree 2, degree 3. Or should have put them here. I guess I wrote them here. But this is a basis for the degree 0 terms. V is just right here, so this is a basis for the degree 1 terms. This product, E1, E2, E1, E3, E2, E3, is a basis for the degree 2, and then we're back to, so you notice 1-dimensional, 3-dimensional, 3-dimensional, 1-dimensional. This is going to be 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Just to write that in general, you're going to have, GV is this direct sum, where this is the degree 0, the degree 1, the degree 2, up to the degree n. The dimension of each of these is going to be, if V is dimension n, it's going to be n choose, whatever this is. So n choose 0, n choose 1, all the way on up. And so we get to the classic committee problem, and combinatorics 101, but great practice. The dimension, the way to form subsets, way to form a committee, it's, to the n, but it also equals the sum of the binomial coefficients. So there's 2 different ways you can pick the committee, and you can think about counting it this way, which is everyone in or out, versus you can think about forming the committees of a certain size and then grabbing the people, and that's what those 2 each are going to equal the same thing. So if you don't know what I'm talking about, look up committee problems. Knowing that 2 to the n equals this sum is a great little intro combinatorics problem. Okay, so I'm going to call out that these, this ascending product, they are linearly independent. So I've talked about spanning so far, which puts an upper bound on the dimension. The proof does take a little more work to show that they're linearly independent, so I may make a video on it. I didn't feel like making this one go longer. We're already at 20 minutes now. It's really good practice. It's a little bit more in the weeds, get our hands dirty, so I'm not sure if I'll make that one or not. But you're more than welcome to, and in fact encouraged to, how would I prove that they're linearly independent? It's not entirely trivial. It's not hard, but it's a bit indirect, and yeah, at least the way I'm aware of off the top of my head to do it. Um, let's just do one quick calculation to end this. So we are in R2. Let's say we got our orthonormal basis E1, E2, and let's just say they're both positive, so they each square to 1. Fine. Let's take a vector C and a vector D. So this is just C1, E1, C2, E2, same with D. Let's just take their geometric product, which I realize I wrote as CV. Probably doesn't mean anything to people these days, unless you're old enough to remember CDs. So if you start just multiplying this out, well, E1, E1, that's going to be 1. So I'm going to get C1, C1, D1, C2, D2, right? These are just become scalars. And then over here, oh, I should put a parentheses around this. Whoop. We get this parentheses where the negative sign is because, we had E2, E1, so we flipped them to get E1, E2, so that's why there's a negative here. And so just to put it together, you see CD equals this. This is a scalar. This is degree 0 plus this. This is degree 2, or what we call a bivector. So notice that vector times vector, it not only, like if this were truly n-graded, that would give me just a bivector. But in fact, in general, it can give anything from, it can give scalar plus bivector. So degree 1 times degree 1 is going to give me degree 0 plus degree 2 potentially. Where depending on C and D, like it could just be scalar or it could just be bivector, and oftentimes it's a mix of both. Welcome to what's going to be what we're going to find in just a second. Parity is preserved, not the degree. So this isn't going to be n-graded. This is going to be our super algebra. This is next video talking about that the geometric algebra, part of its interest is that it ends up being a super algebra, not just an n-graded algebra like, say, the exterior algebra. Also, just point out this is going to be the induced bilinear form. This is going to end up being the inner product. This is going to be the exterior product. And so we're going to get the famous uv equals u dot v plus u wedge v, right? That's what this is. And so we'll get there. I'll introduce this more formally in I think it's right about lesson 10. So we're going to do a few things before we get there, but right here in front of us is that formula. Okay, that's enough for now. Next video is going to be all about this being Z2 graded, being a super algebra. I may make a video on the linear independence. I also may make a video on Yoneda's lemma, realizing that all this other stuff I've been doing with the common categories and things, the category of elements, like they're all just examples of Yoneda in practice. So I may make a video on Yoneda while I've got it fresh in my mind just to call that out. All right, I hope people are enjoying this. Sorry for the length. Until next time, be well.